morning everybody, and let us go through our course on introduction to mechanical micro machining processes. In the last class we have started a new topic, that is the difference between the micro and the macro machining operations, and we have seen some of the things that what is going to happen when you cut a material at the micro scale, and there is one new term that came across, that was called the size effect. So, size effect is something defined like this, that if you reduce the size of any process or any component, how the things will differ, make a difference in terms of the process mechanics or in terms of the operation of a particular component. And we have seen that there are different components or the different parameters which will affect the machining processes, something like a uncut chip thickness and cutting edge radius, and there are different material properties also play important role when you cut material at a micro scale. So, let us continue with the same class. So, in the last class we have seen this particular graph or particular diagram, that where the size effect has influence on this different type of parameters. So, now let us see this thing, that cutting small cutting edge cutting uncut chip thickness has the effect on the low cutting temperature. Then because of the low cutting temperature, the material yield strength is very high, and it results in the high friction coefficients. Now, let us see this now what is the effect of grain size to the chip thickness, that we have seen in earlier slide, that there is a effect of the grain size also. So, now this is the diagram which is the conventional machining operation. Now, what is happening here, that this is our tool and this is the uncut chip thickness. So, let us note it down here. So, this is your uncut chip thickness, that is let us write HC, and this is your cutting edge radius, but right now it is difficult because it is very sharp, but still let us put something like that, this is called R. So, now here if you see HC by R, this one is very large than 1, because your HC is very large compared to the R. So, it removes the material very efficiently, and this is your rake angle. Now, consider this particular thing, whatever this triangle is showing. So, this is called the grain size, this is a single grain. So, this is a grain, correct. So, this is in case of the conventional machining. So, your objective of this figure is to show that your HC is many times higher than the R, and you are efficiently getting one chip which is flowing over the rake face of the cutting tool. And this is the same diagram here, only difference here is this particular grains. Now, if you see, we have not given any type of difference in the cutting tool, alpha is also same, workpiece motion is also same in this case, and we have also not changed the HC. Now, HC is also same here. So, this is the HC. Only one thing has changed here, that is this particular grain. Now, if you see, this is the one grain, but that one grain is become very large here in this case, because our depth of cut is very small relatively. So, now what is happening in this case, now when you are cutting a material at a macro scale, you are actually removing many layers of the grain. So, this is the one layer, two layer, it may be more than 2 or maybe more than 10 also when you do cutting in a macro machining or the conventional machining. But when you do same thing at this particular scale, where HC is in terms of tens of micron and this is in terms of hundreds of micron, then each and every grain orientation, property of this grain, defect inside this grain play important role in the removal of the material. So, here in this particular case, your tool is going to cut the grain. So, this particular grain will come as a part of this grain will come as a chip, and this become the workpiece, because it is going below the cutting tool. So, in this case, whatever energy we have to spend for cutting this material will be very high, because you have to cut the grain. You will not encounter the grain boundary, because when you are cutting at a macro scale or conventional machining, you will easily get the boundary by which your grain will be separated out, so you don't need to cut the grain. But here this type of probability is very less, so many time you have to do cutting of the grain. So what is this thing? The shear deformation occurs within a single grain. So that is what is happening here in this particular case. Stresses applied to the tool are dependent on the individual grain orientation. So now we know that here it is showing very ideal situation, that all grains are oriented and put together in a very particular fashion, but that is not going to happen. This type of particular fashion will not be available when you actually do cutting of a different materials. So now say these are the two different examples. So here this is the small grain size, and here it is comparatively large grain size. Right. So now let us consider this thing as this particular example, that macro machining. So macro machining will not make much difference, because anyhow your cut will be very large. It may pass, because here it is in 25 micron is this much, this scale is a 25 micron. So if you consider 25, this one is the 50 micron. Let us consider this is the 50 micron. So when you cut a 50 micron is a depth of cut, this is called HC. At the time there are many layers, comparatively less, but you may get at least 1 or 2 layers of the grain which will be come out as a chip, and that will be even more easy in this particular case, because in this particular case your HC will be this much, same HC, but you will encounter many types of grains. So getting that particular boundary is very easy in this particular case. But now if you use this particular process here, now let us consider your depth of cut is very small. So whatever is 25 micron is there, so let us cut, this is the 25 micron, and same way it is here, this is also 25 micron, and we are using a micro machining operation for cutting this particular material. Now coming to this part, first this one. So now here, even if you are cutting at a 25 micron depth of cut, still you are able to get the small amount of high probability of getting the grain bound, because size of the grain is even smaller than what we have seen. So here it is 5 micron. So this dimension is a 5 micron. So you consider 25 micron means it will be something like this. So this will be the 25 micron. So in this particular case also you can easily remove the material. But here if you do same thing here at this particular, now what is going to happen here, that you have to cut the grain here. Getting a boundary is very difficult. So what is problem because of this? So first thing is the high frequency fluctuation in the cutting forces. Now why it is going to happen? Now consider this particular part. Now here if you see this boundary has a very linear part. So now consider your tool is located here at this location. So in this particular case it will pass through this boundary, so this whole thing will come out as a chip. But only there is a one problem, that there is a one grain. So this grain you have to cut, because this grain is coming as a one of the, some of the grain, some part of the grain is below the material and some of the grain is located within this HC. So now when your tool is moving in this direction, it is finding grain boundary. So as soon as it initiate the crack or initiate the particular shearing, at that time this whole thing will move very easily. But as soon as it encounters this particular grain, now this whole grain is coming into its picture, and then because of that now you have to cut the grain. So suddenly you have to apply more amount of forces to cut down this thing, because now you are not getting a boundary. There is only way that your tool will jump in this direction, that depends on the stiffness of your machine tool, that we will discuss more detail in the component of the machine tool. But right now we are considered the machine tool stiffness is very high. So in that particular case it will not jump over this part, but it will cut the grain here. So as soon as your grain cutting is, so your forces will be very high in these cases. So here force will be high. Here force will be very high for cutting this much amount of material. As soon as you are passing this grain, then again you are getting a grain boundary here, so it will be very easy again. And by chance in the second instant you again encounter one grain which is half on this uncut chip thickness and half into this, then again you have to apply more force. So your within a single cut, your cutting tool is encountering a different orientation and different part of this part. So sometimes it has to give more amount of force to material, sometimes less. So that is the reason that you are ending with the high frequency fluctuation, because we are going at a very high speed, and that is the reason of the high frequency, and fluctuation is because of the sometimes you need high force, sometimes you need a less force. And because of that, what is happening, that it is instability and the tool breakage, because we know that our tool diameter is also very small, because if you consider the tool, so our tool is something like this. So this is our end mill cutter consider, and this diameter you consider 200 micron. Now when the tool diameter is very small, your effective length of the cutting length is also very small, because you cannot have very long hangover on this part. And now when you are cutting this part, now it is considered it is moving in this direction, and you are getting a one particular boundary here. So these are the grains located here. Let us consider. So these are the grain located here. So it is very easy to remove the material. And now consider there is one grain here at this location. So when it is moving in this direction, at that time suddenly this grain is coming. So at that time you will get instability. Suddenly you have to apply more amount of force. So either your tool will bend little bit in this direction, or it will break from this location, where that depends on the what is the RPM and what is the feed rate you are providing for cutting this particular part. So you are getting instability. Instability means it may bend, but it will not break. It will continue with a machining of that. And tool breakage, that means whatever forces you are providing it, that forces are enough to break this particular slender tool, that is micro tool. So these are the problem when you are talking about the grain size with the chip thickness. Then coming to more very important parameter, that is the uncut chip thickness versus the cutting edge radius. So now in macro scale or the normal machining, we have seen that our uncut chip thickness is many times larger than the cutting edge radius of the cutting tool. So this figure we have seen, and that is what was here. So it is very easy to remove material, many things are there. So this is our uncut chip thickness HC, and you will get a small r here. Let us consider this is the r, right. So this here we can write HC is many times bigger than r. But in micro scale, proportionality is just as large, or sometimes it is very small compared to this part. So this is what is happening in our micro machining. So now your HC is this one, which is even difficult to see also. So this is HC, and R is very large, that we have given here. So in this case, it is HC is equal to or sometimes smaller than the R. Right. So what is because of that cutting force would easily exceed the bending strength of the cutting tool, that we have seen in the last slide, that now you have to apply more amount of forces because your chip thickness is very small, uncut chip thickness, and your cutting edge radius is very large in this case. So your loading on the tool will be very large, because we know that if you want to cut any material with a blunt tool, you have to apply more amount of forces, and if it is a sharp, then your force requirement will be very less. That happens in any type of cutting. So if your blunt tool is you are using, then your force requirement or the amount of force you require to cut the material will be very large, and it ends up in the removal of the or breakage of the cutting tool. Now what is happening in this particular chip thickness smaller than the cutting edge radius? So we know that there is a large cutting, a negative rake angle happens. So that large weight at which location we are considering. So now suppose it is a, this is the cutting edge. So now the chip is moving, your material is moving in this direction, and your shear plane may be somewhere here. This is your shear plane, and this is your chip. So in ideal case or in micro machining, macro machining, conventional machining, what is going, what is the scenario that your chip will flow in this direction, and your uncut chip thickness will be this something like this, and it will be easy to remove the material. But that is not the case here, because our HC is very small here. This is HC, and your R is very large here in this case. So your material deformation occurs at this location. So your rake angle, it is calculated from this location now, not from this location, because the some part of the cutting edge, it will behave as a rake face of the cutting tool, and then you have to calculate this is the effective rake angle, and this is the rake angle of the cutting tool. So now there is a large cutting negative rake angle, that is what is here, this particular part, that increases the amount of cutting forces during the chip generation, because now your blunt tool is coming into action, your cutting forces will be very large in this particular case, that we have seen also. It exaggerates the need for a smaller chip. Now we know that if you reduce the size of the cutting tool, size of the chip, so reducing the size of the chip, that is HC, we can reduce the cutting force, right? So in this particular case, we know that we are ending with the negative rake angle, so forces will be very high. So to counteract this thing, what we have to do, we have to reduce the size of the chip. So smaller chip is required to go through it, and that will result in a light chip load. So chip load will be very light in this particular case. Now we have reduced that thing, so no problem in that case. But there is a problem in the low productivity, because now if you reduce this uncut chip thickness, then if you want to remove very large amount of material, then you have to go through many passes in that case. So now suppose let us use the turning operation. So now this is initial diameter is D1, and then you want to reduce it to D2. Now this is your D2. And this is the amount of material you want to remove. So if you reduce your particular chip load, smaller the chip if you want to reduce, then what is going to happen, that you have to do many cutting here. Maybe 3-4 pass you require to reach to this diameter. But if you use the very large amount of chip, then within 1 pass or 2 pass you can cut the same amount of material. So your productivity is very low in this particular case if you follow this part. So there is one way to encounter this thing, that you have to increase the RPM. So what to do in this case? So here what we have to do, we need very high RPM. RPM or the rotation of the tool. If you give high RPM, then what you can do, you increase the feed rate, because you are able to remove more amount of material by this particular operation. So high RPM requirement is very important to get the high productivity. If you do not do with this thing, then you are end up with the low productivity, because you have to save the tool also, and you have to also get the workpiece in a proper geometry as per the required dimensions. Right. So, there are different type of mechanism when at which the material will flow over the rake face. So, let us go through it. So, first one is the shearing operation. So, now here we know that we are end up with the negative rake angle. So, in this case let us start that at which particular negative rake angle you are getting the chip and at which angle you are not getting chip at all. So, now first example is the condition where the uncut chip thickness is equal to the or little bit smaller than the cutting edge radius. So, now this is the cutting this is the uncut chip thickness. So, this is what it is showing here. So, this is HC and let us give something here. So, if this is the HC, then let us consider this is the R, this is the R and this is the negative rake angle which is happening because of this part. So, here if this is the case, then what are the chances of getting a chip out of this particular operation? So, let us see the what are the conditions or what is happening in this case. So, first thing is that material adjacent to the cutting edge radius is compressed. So, now whatever is your material is coming from here in this direction, that is opposite to the tool motion. So, material adjacent to the tool edge radius is compressed. So, this is the cutting tool edge radius. Let us give some different color. So, whatever is this here, so this is the whole thing is a cutting edge radius, this one. So, material adjacent to the tool edge radius is compressed. So, when you are getting this particular time, some of the material is compressed, displaced upward. So, this is the material. So, this thing is going in this direction, but your material is also flowing in this case. So, some of the things will be displaced in upward direction and removed as a chip by the tool feeding motion. So, if you continue in this direction, so it will create one particular plane, that is shear plane. Above of this particular thing your chip will be removed and some of the material whatever is there, that will come is a, it will again encounter in the next one. So, if you continue this motion in this direction, some of the material is removed, but some of the material will take some time and after second instant or third instant it will come out as a chip. So, tool acts as a strong source of the dislocation. So, this is the particular tool edge. So, this tool edge, because obviously the tool is the only thing which is sharper compared to other location. Even it is a blunt looking like here, but it is comparatively sharper than the other edges around the tool. So, this will create as a behave as a one of the source of the dislocation, through which it will create a one fine crack. So, this fine crack will start from this particular point. So, this is one arbitrary point we have found that on this particular things you consider this is your uncut chip thickness region in this particular line and then it will initiate a primary shearing process. So, this is the way it will. So, this is your shear angle and this is your shear plane and your S is this particular point. So, let us continue further in this. So, now here in this case whatever the material ahead of the tool is pushed in the direction of the motion, right. So, material is coming in this direction and this your tool is moving in this direction. So, material ahead of the tool edge. So, this is your tool edge that we have seen in the last slide also. So, this is the tool edge. It pushed against the in the direction of the tool motion. So, this is in the direction of these are the material because your workpiece is coming from this direction. So, whatever is the material which is considered within the zone of HC, that is going to push in this direction because now it is not the sharp, your face, that is the rake face, is located on the negative side. If it is in this direction, then the flow of material is very easy in this direction, it is very facilitated, but it is not the case in this case. So, now a shear band is developed joining the top of the tool and the surface of the work material. So, now this is a shear band. So, this is the one shear plane it will generate because it is not located very easily, because everything depends on the what is the depth of cut, what is the feed at which you are moving the workpiece, what is the RPM of the cutting tool, and everything depends on that. So you will find one location where you will get the shear band developed in this case. So this will be a very little amount of area which is given here, and by which you can get the something done as a chip. So a narrow zone of the shear originates at the location of the tool tip and separate as a chip. So now we know that this all material is going inside the, this all material whatever is here, these all the things, so whatever is here in this case, these all things is pushing towards the motion of the tool, but your material is continuously moving in this direction. So because of that, your chip, you are getting one particular instant at which it will generate a shear band, and some material will come out as a chip. Now see, the chip location is this one, still some material is here in this case. So in the next instant, when you continue this operation, your tool is somewhere here. So this is the second instance of your tool. So whatever is this material become a chip here, and then this particular material come to this particular place. So in this case, if you continue in such fashion, so at that time you will get a small amount of material as a chip, and then remaining material may go inside the material also, or it will continuously do a sequential machining in terms of this operation, that some part become a chip, then this particular portion will take place of the chip, and then remaining portion will come to this place. So in that way you can get the material removal by means of shearing. So shearing is the important thing, because we want shearing happen for all the things, whatever is the HC is there. So we want that HC should be removed in shear mode, right? This is what is important in this case. So everything depends on where we are locating this S here, because if S is located somewhere here, you will not get this thing also. So that things we will discuss in the next class, because now we have to shift this S in such a way in the downward position, so that your alpha become more and more large in this particular case. So that things we will discuss in the next class, and let us stop from this slide. Thank you very much.